Welcome to a deep dive into, well, one of the most critical parts of building advanced AI, how we actually create the high-quality data that gives these models their reasoning power.
It's often a bit of a black box, isn't it?
Totally. Okay, let's unpack this because, large language models are getting better incredibly fast.
Mm.
But the specific recipes, the details for training, the very best ones, especially those good at complex stuff like math or coding or science problems.
Yeah, those tend to be kept pretty close to the chest by the big labs.
Exactly. And that lack of transparency, it makes it really tough for, the wider research community to figure out what actually works and to push things forward themselves.
Which is why this paper we're looking at today is so interesting. It's from the Open Thoughts Project.
Right. And they're trying to sort of pull back the curtain, systematically looking at how to create the best training data for reasoning models, specifically using supervised fine-tuning or SFT.
Mm-hmm. And what's really fascinating here, I think, is the focus. It's not just about bigger models or new algorithms, although those matter. This project highlights that the data itself, the stuff you train on, is just a massive lever for performance.
It's like realizing the ingredients are maybe even more important than the fancy oven you're using.
Precisely. It shifts the focus in a really important way.
So our mission for this deep dive is to walk through these open thoughts experiments. They tested all these different strategies for creating SFT data to see what really moves the needle.
We're getting a peek inside the AI kitchen, basically, focusing on those ingredients.
Okay, so these powerful models, they usually start with a pretty broad base from initial training, right? But the specific skills, especially solving problems step by step, that often comes later.
Exactly. That comes from post-training techniques like SFT. It's that fine-tuning phase using this carefully curated data where they learn to generate those detailed internal steps, those thinking
It's
tokens.
the ones that guide them to the answer.
Mm-hmm. And we've seen this work before. Projects like R1 Distill, for instance, they got really strong performance. What was it, 51% on AA math?
Yeah, and like 33% on GPQA science questions.
Yeah.
Impressive stuff.
Right. And that was just with SFT on good data. They skipped the whole expensive reinforcement learning part entirely.
So this open thoughts paper really doubles down on just how crucial that high-quality SFT data is for reasoning.
Definitely. And recognizing that it's super expensive and complex to just guess what worked.
Yeah, the design space is huge.
The Open Thoughts team took this really systematic approach. They ran through, what, 4 generations of refining their data creation process.
Yeah, culminating in the OpenThoughts 3 1.2M dataset and the OpenThinker 3.7b model.
And crucially, they're releasing it all openly. The findings, the data, the model, that's a big deal for the field.
So how did they do it, this systematic approach?
Well, it's pretty clever. It's like running a controlled experiment on each part of the data pipeline. Figure 2 in the paper lays it out nicely.
Yep.
They broke it down. Sourcing the questions, mixing different sources, filtering those questions, deciding whether to get multiple answers per question, filtering those answers, and even picking the teacher model that generates the solutions.
And they tested strategies for each step.
Yeah, at a manageable scale first, maybe around 30,000 data points per experiment to see what actually worked best before scaling everything up. Isolate the variables.
Smart. Okay, let's get into the findings then. Step 1, question sourcing. Where do you get the problems? They looked at tons of sources, right? Code, math, science.
Yeah, dozens. Synthetic ones made by AI, semi-synthetic, human-written stuff from coding sites, math forums, science papers. A real mix.
And what was the big takeaway there? Did complex sources always win?
Interestingly, no. Some of the simpler, purely synthetic methods actually perform just as well, sometimes even a bit better, than the more complex or hand-curated ones. But the really striking thing was just how much the source mattered. The performance difference between using the best source versus the worst source for, say, code problems was huge, like over 17 points difference.
Wow. So choosing where your questions come from is step 1, critical.
Absolutely critical.
Okay, now here's one that really caught my eye. What about mixing those sources? You've got a few good ones. You think, okay, let's mix them all together, more diversity.
Right. That's the intuition, isn't it? More variety should make the model more robust. But their findings were pretty counterintuitive here. Mixing lots of different question sources actually hurt performance.
Seriously.
Yeah. The best results came when they mixed at most 2 high-quality sources
Only 2.
across all domains, math, code, science. It really suggests that the quality of those individual sources is paramount. You can't just throw a bunch together, even if they're decent. Quality over quantity in the mix.
Fascinating. Okay, so you've carefully picked and maybe mixed 1 or 2 sources. What about filtering out bad questions, getting rid of noise?
Yeah, filtering definitely helped. That step did improve performance. They tried a few technical ways to do it.
Like what?
Things like using text classifiers, looking at embeddings. But what seemed to work relatively well across the board was using another AI model, like a smaller GPT-4o version, to sort of evaluate the questions.
Like asking an AI, is this a good, difficult question?
Basically, yeah, either judging quality directly or assessing difficulty. That seemed to work pretty consistently.
Okay. They also looked at deduplication, making sure you don't have repeats, and getting multiple answers for each question.
Right, deduplication is important so the model doesn't just memorize. And the multiple answers thing, especially for math, that turned out to be quite beneficial.
How so?
They found generating multiple solutions. I think they tried up to 16 different reasoning paths from the teacher model for each math problem, and including all of those in the training data actually boosted the final model's performance.
So seeing different ways to solve it helps the student model learn.
Seems like it, yeah. Giving it more diverse examples of the process.
Okay, but then what about filtering those answers? If you have 16 attempts from the teacher, surely you'd want to pick the best one, or the shortest, or maybe use majority rules.
You'd think so, right? Apply some quality control there too. But another one of these intriguing findings.
Let me guess, it didn't help.
Exactly. Filtering the generated answers, things like removing really long ones or trying to verify answers using consensus, it didn't improve performance compared to just using all the answers generated by the teacher.
Huh, so just showing the model all the different attempts, warts and all, was better.
Apparently so. Maybe seeing the less than perfect paths is also informative somehow.
Wild. Okay, last piece of the pipeline. The teacher model itself, the one generating the examples. Did it matter which big model they used as the teacher?
Oh, absolutely. Big difference. They compared a few powerful models.
And the winner was?
QWQ32B, which is based on Qwen 2.5, came out on top in their setup. It was a bit better than DeepSeek R1, another strong contender, and significantly better than some others they tested.
So the quality of the teacher generating the reasoning steps is clearly critical.
No question. Garbage in, garbage out, even if the garbage is still a pretty smart AI. You need a good teacher.
Let's circle back to those reasoning steps themselves, the thinking tokens. How vital are they? Does the model need to show its work internally?
Critically important. That was one of the clearest findings. Explicitly training the model on these step-by-step reasoning traces consistently led to huge performance jumps.
Like how big?
Well, on that tough AIM math benchmark, accuracy went from something like 2% without explicit reasoning.
Wow, basically guessing.
Yeah, to over 45% when the reasoning was enabled and trained on. A massive difference.
And it learned this behavior pretty deeply.
It seems so. They even tried prompting the model without the explicit show your thinking template, and interestingly, it often started generating thinking tokens anyway.
Like it knew it needed them to solve the problem.
Exactly. It suggests the model learned that this internal reasoning process is necessary for tackling complex tasks.
Okay, but what if you try to make that thinking more efficient? Like, trim it down. Remove the parts where the model seems to be reflecting or correcting itself.
Yeah, they tested that too. Can we make it shorter, remove self-reflection, filter out really long thought processes?
Yeah.
It significantly harmed performance. Like, removing just the self-reflection parts dropped the average performance by almost half.
Whoa.
Yeah. It really strongly suggests that those detailed, sometimes long and winding reasoning structures, including self-reflection, aren't just fluff. They're essential for the model to get the right answer consistently on hard problems.
So don't rush the thinking process.
Pretty much. Let the model think it through even if it looks messy.
Okay, so they took all these winning strategies, best sources, minimal mixing, filtering questions, multiple unfiltered answers, best teacher, full reasoning, and built the big OpenThoughts 3 1.2M dataset. Did scaling up with this optimized recipe work?
Absolutely. They showed a very clear, strong, positive correlation. As they used more data created with these successively better pipeline choices, the model performance kept climbing.
The scaling curves shifted upwards.
Exactly. The final dataset is over 1 million examples, heavily weighted towards math, which seemed effective, but still with substantial code and science components too.
And training on this big, carefully curated dataset gave them the OpenThinker 3.7b model.
That's the one. And again, the big contribution is making both the dataset and that model openly available. It's a real benchmark now for open reasoning models.
Now, evaluation is key. How do they make sure the results were fair?
They used a whole suite of standard benchmarks covering math, code, and science. Things like AIM, Math 500, Codeforces, Live Code Bench, GPQA, established tests.
But the elephant in the room with benchmarks is always contamination.
Right.
How do you make sure your training data didn't accidentally include test questions?
Crucial point. Yes, decontamination. They were quite rigorous about it.
How'd they do it?
They use techniques like fuzzy string matching and looking for overlapping grams, basically.
Yeah.
Sophisticated ways to check if any part of their training data looked suspiciously similar to any question in their evaluation sets.
And was it effective?
Very. Their method caught something like 99.6% of samples they knew were contaminated in a test, while only wrongly flagging about 1.4% of clean data. So it was precise.
That's essential for trusting the results. You need clean benchmarks.
Absolutely. Otherwise, you're just measuring memorization.
So after all this impressive, meticulous work, where do these open models, like OpenThinker 3, stand? Have they caught up to the absolute cutting edge, the proprietary models?
Not quite yet. OpenThinker 3 definitely pushed the state of the art for open models significantly. That's a huge achievement.
But there's still a gap.
Yeah, their own results show there's still a noticeable performance gap compared to the frontier models, like, say, Gemini 2.5 Pro. The best closed models are still ahead.
Okay. Now, this whole process, focusing intensely on reasoning, does it create any, side effects? Any trade-offs? What about safety, for example?
That's a really important question, and they did look into it. They ran safety evaluations.
And what did they find?
Well, OpenThinker 3.7b showed a somewhat higher rate of generating harmful content on a standard benchmark compared to the base model it started from,
Oh, interesting.
and also higher than another distilled reasoning model, DeepSeek R1 Distill. However, it also refused to answer potentially problematic but harmless questions more often than DeepSeek.
So a mixed bag on safety.
Kind of. It suggests that this intense training for reasoning might introduce some complexities or trade-offs regarding safety. Or, at minimum, it highlights that you probably need specific, dedicated safety alignment work alongside the reasoning training. It's not automatic.
Right. And another potential issue, generalization. How well did these models handle problems that are just slightly different from what they trained on?
Yeah, that's another area they flagged as needing more work.
What did they see?
They observed that their distilled model, OpenThinker 3.7b, showed some brittleness in zero-shot generalization. If you give it simple variations of problems it hadn't seen, its performance could swing quite a bit.
Whereas the frontier models were more stable.
Much more stable on those same variations, yeah. So it indicates these distilled models haven't yet achieved that really robust ability to generalize to even simple, unseen problem structures.
Still work to do there. And finally, the practical side. Doing all this, creating the data with powerful teacher models, training the final model, that takes serious compute power, right?
Absolutely. The compute costs are significant. They laid it out in the appendix.
How much are we talking?
Thousands of GPU hours just to generate the answers for the dataset using the teacher model, and then tens of thousands more GPU hours to actually train the final 7B model. Even their smaller pipeline experiments weren't cheap.
So while the focus is on data, the compute barrier is still very real.
Very real. It's a major bottleneck for many researchers trying to work at this scale.
Okay, so wrapping this up, this deep dive into OpenThoughts, it really paints a clear picture, doesn't it? Building better reasoning AI isn't just about bigger models or fancier algorithms.
No, it's fundamentally, powerfully about the quality and the incredibly careful, systematic curation of that training data, especially for SFT.
And what's fascinating is how those systematic experiments threw up some real surprises.
Totally. Like finding that mixing only one or two high-quality sources is better than jamming lots together, or that filtering the generated answers didn't actually help. It challenges some common assumptions.
Yeah, it shows the value of actually testing these things empirically.
And the fact they shared the data set and the model openly is huge. It gives the whole community a solid baseline and tools to build on.
Absolutely.
Yeah.
But it also clearly shows the road ahead, right? Closing that gap to the frontier models.
Improving generalization, definitely. Figuring out the safety trade-offs and how to manage them.
Maybe exploring if other methods like RL are still needed on top of SFT.
Right. And, of course, tackling that huge compute cost to make this kind of research more accessible.
This whole exploration has really highlighted the just meticulous, experimental, and sometimes surprising work that goes into creating the data that powers AI reasoning.
It's a great reminder that even with cutting-edge AI, the ingredients, the data, are just as vital, maybe even more so, than the cooking method.
So what does this all mean for you, the listener? I think it means understanding that AI capabilities aren't monolithic. They're built layer by painstaking layer, and that data layer is incredibly complex and well, crucial.
And it does raise a bigger question to think about, doesn't it? If optimizing for one capability, like reasoning, requires these very specific data recipes, and those recipes might introduce challenges in safety or generalization,
Yeah.
how do we make sure that future AI development effectively balances pushing those advanced capabilities with ensuring the resulting systems are also robust, reliable, and safe for everyone?
That balance is key. Definitely something to mull over as these incredibly powerful tools become more and more part of our lives.